Now I want to introduce you to what's called function notation. Most of the time, instead of writing y equals whatever the expression is, we replace the y with this f parentheses x notation. This is called function notation, and all this is a labeling system. Now when we read this, I know it might look like multiplication to you. It kind of looks like f times x, because we do frequently use parentheses as multiplication indicators. But here, this f is not a variable. So this is not representing multiplication. This f is a label. Think of it like a name tag. And so when we read this, we say f of x. We never say f times x. Again, this does not represent multiplication. So when you read this, you say f of x. And the f, again, is just a name or a label for the function. So notice that the f of x takes the place of the y variable, but whatever you calculate here is still going to give you the y part of an ordered pair. It's just that you don't see the y, you see the f of x label in its place. The reason that we like to use this notation is because if you're dealing with more than one function and they're all labeled y, it can get confusing. So if we had two different functions we were working with, one of them might be f of x and the other one might be g of x or h of x. So we just give them different names so we can tell them apart. And the x here is to let everybody know what the variable is here. Now you might look at this simple one and say, well, it's obvious that the variable is x. I mean, what else could it be? But in higher math and in more sophisticated sciences, a lot of times a function will have more than one variable, and there might be symbols in the expression that are constants that are not variables. Like think of the pi symbol. That's really a Greek letter that represents a number. It doesn't change. It's not a variable. So really what this parentheses does is it lists all the things that can be variables in this expression. And we would say that f is a function of x because when x changes, the value of the function changes. In other words, the y value changes. And so the x here becomes a way to keep up with what we've plugged in to get the function value. So we'll replace this x with whatever number we're plugging into the function. I'll show you how that works. Okay, here's example 6, and this says let f of x equal negative x squared plus 5x minus 3, and let g of x equal 2x plus 3. And we want to find each of the following and simplify if possible. So here in part A we have f of 2. So what this means is take a 2 and plug it into the f function. Now when you plug that 2 in, it's no longer f of x, now it's f of 2. So I'm going to write f of 2 equals negative 2 squared plus 5 times 2 minus 3. So make sure you notice that. If I plug in a 2, this is no longer f of x, now it's f of 2. And I just need to calculate this. So think about your order of operations. Remember PEMDAS. We have to do exponent operations before we can deal with multiplication. Attaching this negative to the 2 is a multiplication step because really what you've got here is negative 1 times 2. But this exponent is not affecting the negative. So first we do the exponent and we say 2 squared is 4. So we're going to have here negative 4 plus 5 times 2, which is 10, minus 3. So negative 4 plus 10 is 6, and 6 minus 3 is 3. So we just found out that f of 2 equals 3. Now let's do f of q. So to find f of q, we plug a q in. Notice it was f of x, and we had x's here. If we now make it f of q, we'll replace the x's with a q. So we're going to have negative q squared plus 5q minus 3. And there's really no simplifying you can do here because q is just another variable just like x was. And so we have to leave this one in this form. And now let's look at part C. Here we have g of a plus 1. So this time we're going to the g function and we're plugging in the expression a plus 1. Now look at the g function. It says g of x equals 2 times x plus 3. Here we've replaced the x with the expression a plus 1. So g of x becomes g of a plus 1, and therefore 2x becomes 2 times a plus 1. So 2x plus 3 becomes 2 times a plus 1 plus 3. Now it said simplify if possible, so we need to distribute this 2. That's going to give us 2a plus 2 plus 3. And then we need to combine our like terms, so that's going to give us 2a plus 5. Now here's another practice problem, and I would really encourage you to pause the video here and try this one by yourself before you watch the answers. And assuming you've had a chance to do that, now let's go through it together. So we start off in this example with f of x equals negative 3x plus 4, and g of x equals negative x squared plus 4x plus 1. In part A, it says find f of 2m minus 3. So we're going to be using the f function. We are replacing the x with all of this. So negative 3x plus 4 becomes negative 3 times this stuff plus 4. You see how the 2m minus 3 takes the place of the x? Negative 3 times x becomes negative 3 times this stuff. So now if I distribute the negative 3, I'll have negative 6m plus 9. Don't forget the plus 4 out here. And then combining like terms, 9 plus 4 is 13. So we're going to end up with negative 6m plus 13. Then in part B, we have g of negative 2. So we'll be using the g function, and we're replacing the x with negative 2. So g of negative 2 is going to equal negative 2 squared plus 4 times negative 2 plus 1. Now again, remember you have to do your exponents before you deal with this negative. We can't say negative times negative 2 is positive 2 yet because we have to do the exponents first. Negative 2 times itself will be positive 4, and then this negative is still there. So on the next line we're going to have negative 4 plus 4 times negative 2, which is negative 8, and then plus 1. And now negative 4 minus 8 is going to be minus 12, and minus 12 plus 1 is negative 11. Okay, now we're going to look at some functions that may be in different forms. So far in this section we've seen functions that are written as ordered pairs, functions that are written in mapping notation, functions that are represented by a graph, and functions that are represented by an equation. So we're going to be evaluating f of 3 for all of these different types of functions. This first one we are familiar with. This says f of x equals 3x minus 7. So if they ask us to evaluate f of 3, that's no problem. We just plug in a 3 where the x was. So f of 3 equals 3 times 3 minus 7. That's going to be 9 minus 7. That's 2. So in this case, f of 3 equals 2. Now when you've got a set of ordered pairs, you might think, well, I don't know what to do now. There's nowhere for me to plug in my number. But really all you have to do is read. Remember, the 3 is an x value. So when they say find f of 3, they're saying find the y value when x equals 3. Well, if you just look at this list of ordered pairs, when x equals 3, y equals 1. So in this case, f of 3 is 1. It is really that simple. And because this is a function, we know that 3 can only match one y value, so we never have to worry about it occurring twice. And here on the last two parts, we are still finding f of 3. So here is a function written in that mapping notation. So in this case, when x is 3, y is 5. So in this function, f of 3 equals 5. And here in part D, we have a graph. And so the question is still the same, find f of 3. In other words, when the x is 3, what is y? Well, if I go out here to where x is 3, I can find out that when x is 3, y is 4. So in this case, f of 3 equals 4. And it is just that easy. Now it's possible to have an equation that is written in terms of x and y and not expressed in function notation. So when that happens, if you need to express the function in function notation, what you can do is just solve for y and then replace the y with f of x. And that's what we're going to do here in example 8. It says, assume that y is a function of x. Rewrite each equation using function notation. So we will solve for y and then replace the y with the f of x label. And then they're going to ask us to evaluate f of negative 2 and f of p. So in part A we have y equals x squared plus 1. And notice that this one is already solved for y. So really all we have to do here is replace y with f of x. And so our function notation reads f of x equals x squared plus 1. So now to get f of negative 2, of course we replace the x with negative 2. And so we have negative 2 squared plus 1. Notice the negative 2 is in parentheses because the function says that x should be squared. If I'm replacing the x with negative 2, I need the whole thing to be squared, even the negative, so it must go in parentheses. So negative 2 squared is going to be positive 4, and then positive 4 plus 1 is 5. And let's get f of p. So if f of x is x squared plus 1, then f of p is going to be p squared plus 1, and there's no simplifying we can do here, so that's the end of that. Now let's look at part B, and you'll notice that what's different here is that our equation is not solved for y, so we can't just simply substitute the f of x notation in there. First we have to isolate the y. So I'm going to subtract x from both sides. That's going to give us negative 4y equals negative x plus 5, and then I'm going to divide both sides by negative 4. So when we do that, it's going to look like this. The negative 4's here will cancel, and that will leave us y equals, and then this right side is just negative x plus 5 all over negative 4. Now this is okay, and MyLabs Plus will accept this as the correct answer. And it is correct, but it's not in a very nice, easy to use form. A better thing to do would be to eliminate the negative in the denominator. So what we're going to do is multiply top and bottom both by negative 1. And remember, this is just cosmetic. This is just to make the bottom number positive. So when we distribute this negative 1 through the top, we're going to get positive x minus 5. And in the bottom, negative 4 times negative 1 is positive 4. See how that just looks easier to use than this version did, but they are algebraically equivalent. So now I have y equals x minus 5 all over 4, and I'm going to replace the y with f of x, and now we're going to evaluate f of negative 2 and f of p. So if I put in negative 2 here, f of negative 2 is going to be negative 2 minus 5 all over 4. That's negative 7 over 4. And then f of p means I just replace the x with a p, and f of p is going to be p minus 5 over 4. And that's it. And here are a couple of practice problems for you to work on. I would really encourage you to pause the video and try these on your own before I go through the solutions with you. And now I'm going to go ahead and work them with you. So here we have x plus 3y equals 12. Let's first isolate the y. So we're going to subtract x from both sides and divide both sides by 3. And in this case, the denominator is positive, so this is about as nice looking as this one can get. So at this point, I'm going to go ahead and take the y out and replace that with f of x. And now I'm going to evaluate f of 3. So I'm going to replace x with 3. Alright, so f of 3 equals negative 3 plus 12 all over 3. Negative 3 plus 12 is positive 9, so now I have 9 over 3, and that reduces to 3. And then they've asked us to find f of p as well, so if I just plug p in here, f of x was negative x plus 12 all over 3. F of p is going to be negative p plus 12 all over 3, and that will not simplify. And now let's look at this one. Here we have y plus 2x squared equals 3 minus x. And again, the first step is to isolate the y. So all we have to do is move this 2x squared over to the right side. That's going to give us negative 2x squared plus 3 minus x. Now you could mess with the order of these terms. You maybe could put the minus x first and the plus 3 on the end. That's just cosmetic. So this is okay, and you can reorder the terms if you like. And now I'm going to replace the y with the f of x label. So we're going to have f of x equals negative 2x squared plus 3 minus x. And let's go ahead and evaluate f of 3. So if I plug a 3 in here, f of 3 is going to be negative 2 times 3 squared plus 3 minus 3. Now remember, you have to do your exponents before you do your multiplying. So 3 squared is 9. That's going to make here negative 2 times 9 plus 3 minus 3. Negative 2 times 9 is negative 18. And negative 18 plus 3 minus 3 just adds up to negative 18. Now let's get f of p. So if f of x was negative 2x squared plus 3 minus x, then f of p is going to be negative 2p squared plus 3 minus p. Now we're going to talk just a little bit about how to tell where a function is increasing, where it's decreasing, and where it's constant. So first we have to determine what we mean by these words. A function is increasing over an open interval of its domain if the graph rises from left to right on the interval. So look at this graph. From x sub 1 to x sub 2, this graph is increasing. It's actually increasing everywhere, but it's increasing, and you can tell because it's going uphill. In other words, as you move to the right, the y values get larger and larger. So that's what we mean by increasing. And notice that whenever we talk about increasing, decreasing, and constant, we're always using an open interval. So that means no brackets, parentheses only. Brackets indicate a closed interval because the numbers on the end are included in the interval, and you can close it off. But an open interval doesn't exactly have an end because you can always move a little closer to that number without including it. And so when we have an interval with parentheses, we call that an open interval. Okay, now a function is said to decrease over an open interval of its domain if the graph falls from left to right. So if you look at this graph, the graph is going downhill. So over the interval from x1 to x2, the y values are decreasing. So we would say the function is decreasing here. And a function is constant over an open interval of its domain if the graph is perfectly horizontal on that interval. So here's example 9. This says the figure below shows the graph of a function. Determine the largest open intervals of the domain over which the function is increasing, decreasing, or constant. Okay, remember the open interval means there will be no brackets here, only parentheses. And now let's first see if we can figure out where the function is increasing. Okay, it's increasing right here where it's going uphill. You can tell here it's going downhill as we move to the right, and then it reaches this lowest point here, this minimum, and then it goes back uphill until it levels off. What we need to do is tell what the x values are where it's going uphill. So from x equals negative 2 until x equals 1, this function is going uphill. So we would say this function is increasing on the interval negative 2 to 1. Remember, when you say where a function is increasing, decreasing, or constant, we always describe that as part of the domain. So these are x values. The increasing tells us that the y values are getting bigger, but the x values tell us where along the graph the y values are getting bigger. Okay, now decreasing, if you look for where the graph is going downhill, this left half of the curve, it's going downhill as we move to the right. See that? Now, where did it start going downhill? Well, this arrow indicates that the graph goes this way forever. So you could say as far back to the left as you can imagine, it was always going downhill, and it goes downhill until it reaches x equals negative 2. So we're going to say that the function is decreasing on the interval from negative infinity to negative 2. And then where is it constant? It's constant from where x equals 1 until x equals infinity, because it's going to stay horizontal after that point. You can tell by the arrow. So the graph is constant on the interval from 1 to infinity. Now we're going to get plenty of practice on the concepts of increasing, decreasing, and constant in some later sections, but here we're just getting a little introduction to it. So you'll see some homework problems like this in your homework. And it's really not that difficult as long as you remember that your intervals here need to be x values. These are pieces of the domain. So these are always x values. And they're always open, so they always have parentheses. All right, I'll see you guys in the next section.